Okay, welcome back, Physics 30s, to our next lesson in Chapter 7. This is 7.6, and today we're going to be talking about fission and fusion. Have you ever felt so busy or so overwhelmed with things going on in your life that you feel like you're about to explode? Imagine this person that has all these different thoughts going on in their head. Your assignment is due tonight from your teacher. Sorry, you're cut. Better luck next year from your coach. Sorry, we're reducing your hours at work from your boss, and I think we should see other people from now your ex. With all these thoughts going around in their head, this person might be considered unstable or close to a breaking point, and any little thing could set them off. And say they check their phone and it says, your favorite sports team has just been eliminated from the playoffs. This is the last straw, and this person begins to feel infuriated until all of a sudden they just explode. This is sometimes referred to as having a meltdown, and it actually kind of relates to what's going on in nuclear fission. Consider this rather large nucleus. It's got a lot of repulsive forces from the protons pushing against one another, and this is considered to be unstable. The nucleus can barely stand this and barely keep itself together. Then if we shoot just one more neutron at this atom and it gets one neutron bigger, the nucleus can no longer take this and it explodes. The products of the explosion are smaller nuclei, neutrons, and energy. This is called a fission reaction, and it creates two more stable nuclei along with other neutrons, and again the release of energy. Because this has become more stable and energy is released, these products will have less mass because they lost energy. An example where this happens is with uranium-235. If it gets hit with one more neutron, it goes to uranium-236 for a moment until it breaks apart into smaller daughter nuclei, neutrons, and again, a lot of energy. Now what's interesting about this is one neutron caused this nucleus to explode. And now we have an explosion with three more neutrons that have been created. And if there are three more uranium-235 atoms close, these neutrons could go hit those nuclei and cause their own explosions. Then each of those could send out three more neutrons and we would get a chain reaction. This creates a ton of energy and is used in both nuclear power plants and nuclear bombs. A nuclear power plant is definitely more useful and ethical to use this nuclear reaction, but we want to make sure we know how to prevent this nuclear reactor from becoming something like this. So we want to make sure this chain reaction is regulated. How could we do that? Well, what we could do is we could remove some of these neutrons. So we could put in control rods that are going to absorb some of those released neutrons. This would make it so only one of those nuclei explode. It also gives us the advantage that if we want to stop the reaction, we can fully put in the control rods and absorb all the neutrons to stop the reaction. The other thing we can do is we can just have less of these radioactive nuclei around so that it's not as likely that a neutron's going to hit them and we get a slower rate of reaction. So let's take a look at some notes for nuclear fission. It's when an unstable nucleus breaks into two more stable ones. This can be initiated with the addition of a neutron. In becoming more stable, energy is going to be released. Now this will be in the form of kinetic energy of its parts, and there's also often some photons that are released. More neutrons are often released, as mentioned before, which could potentially lead to a chain reaction. An uncontrolled chain reaction is very dangerous, but a controlled chain reaction can be used for nuclear power plants. Questions in this course are often going to relate to energy, and it's going to be similar to the mass defect questions we saw before. So here's an equation with a uranium-235 nucleus reacting with a neutron to make two daughter nuclei, or atoms here, and it also produces two neutrons. It creates a variable amount of neutrons. How you'd solve questions like this is we'll take the total mass that we have at the start and the total mass that we have at the end. We'll subtract the mass that we have at the end from the mass that we had at the start to find the mass defect. Once we have the change in mass, then we are going to plug into E is equal to mc squared to get the amount of energy that is released in this reaction. There's another type of nuclear reaction called nuclear fusion. This is the opposite of fission. Fission was breaking apart. Fusion is fusing or sticking together. So we take smaller nuclei, send them very quickly at each other, and try to get them to stick. So we send these together at a very fast rate, They collide, release a ton of energy, and are then bonded together in the products. So nuclear fusion is when small nuclei collide with high energy and are able to bond together to a new nucleus. This may occur over multiple collisions and eject multiple protons, beta particles, neutrinos, and gamma rays. For example, in the sun, this doesn't happen in just one collision. There's multiple collisions to turn hydrogen into helium. But nuclear fusion is what's occurring and powering the sun. We can see from the sun that this gives off a lot of energy, more than nuclear fission. As we see here, the products are more stable and the reaction produces more energy than fission reactions. This can only be achieved though under very high energy conditions to get those nuclei going fast enough and get them to bond. This is extremely difficult to achieve on Earth. The sun has a lot of pressure and a lot of heat to cause this to happen. So due to its difficulty, we're not yet able to operate fusion power plants here on Earth. However, we can use the energy that's being released from the fusion reaction going on the sun using solar panels and things like that. Now, you may be wondering how splitting atoms and combining atoms can both give us energy, and it has to do with the binding energy per nucleon. This graph shows the number of nucleons down on the x-axis, so we are increasing in atomic mass as we move to the right. Now, what we have on this side is we have the average binding energy. Now, I know we normally put this as negative, but this graph has it as positive. So as we go up, we're getting more and more binding energy, which would mean it's becoming more stable. Again, we normally treat this as negative, but this graph has it as a positive. So this means the highest binding energy would be the most stable. That means that right here at the peak of this graph, we see iron, and this is the most stable element. All other elements have a lower binding energy. So if we were to turn any of these elements into iron, the binding energy would go up and energy would be released. Similar to any of these elements going down to here, becoming more stable, would release energy. So to move in this direction, we have to increase the number of nucleons. So that's why if we collide smaller elements, fusion moves in this direction towards a more stable nucleus. And then fission would go in the opposite direction. We begin with heavy elements, and then we break them apart into smaller ones that are more stable. Both of these types of reactions give off a lot of energy, but we can see that the energy jump in fusion is significantly more than the jump from fission. So that's it for our introduction to fission and fusion reactions. Thank you so much for watching this video, and I'll see you in the next lesson.